Hi, I'm Alessandro. First, let me tell you a little bit about myself. I do research on computer science, specifically in cryptography and computational complexity. I spend most of my time as a professor in computer science at UC Berkeley. I have also worked on startups. I was a founding scientist of Zcash. Zcash protocol is something I worked on while I was doing my PhD at MIT some years ago with my colleagues. And more recently, I've been working also at this startup called StarkWare, where I'm a chief scientist in the West. And so tonight, I'm going to tell you about two topics. One is a technology, the science behind the technology that we work with at StarkWare, specifically STARKs. So I'll try to convey a little bit about where they come from. First and foremost, what are they? And second of all, a little about their construction. It's actually not that hard. It will be done primarily through pictures. And so that will be the first half an hour, which I'm going to time on my cell phone, because I also want pizza in the break. And then, if there is interest, I do have a separate talk about a recent work in SNARGs, a paper called Marlin, something that is already online. There's code available for. You can also play with it. And it's about an efficient construction of a SNARG with a universal setup. I will explain all of this later, but just as a preview. Before I get started, are there any questions about the plan or me or other things? No? OK, so let's get started. Great. So first, I'm going to talk about STARKs. STARKs are a type of cryptographic proof that has particular properties. And by virtue of having these particular properties, it sits in a particular place in what we would call the ARG-scape. Okay? ARG for arguments. These are cryptographic proofs, how we call them. Okay? So, by the way, does anybody know what is an argument? No? Does anybody know what is a proof system? So proof systems are protocols that we use in computer science between a prover and a verifier that are used to demonstrate computational statements. I'll say a little bit about that later. But essentially, it says they are protocols that demonstrate correct execution of computations with nice efficiency of privacy properties. Okay? In cryptography, we study so-called arguments, which are proof systems that are secure under cryptographic assumptions. So essentially, the security guarantee that you get as a verifier is that either the computation was done correctly or somebody broke cryptography. So these are not information theoretic constructs. They have some security. We call these things arguments just to distinguish them from proof systems. So proof systems are an example of arguments. So if you're familiar with some classical zero-knowledge proofs, those are proof systems. A lot of the sort of blockchain technology today deals with argument systems that are so-called succinct. These are proof systems where you demonstrate that a computation is done correctly via a proof that is very, very small. It doesn't grow with the computation that you're attesting to. So whether you're attesting to a computation that consists of 1 second of computation, an hour of computation, 1 day of computation, 10 years of computation, you still get a tiny, tiny proof that certifies its correctness. So, okay? So we denote this property called succinctness. Okay? And over the past 10, 15 years, there's been a lot of work in the theory and practice to construct succinct arguments. These are very useful, even from a scientific standpoint, if we do research in cryptography. But more recently, these things have become rather useful as a technology, specifically in the blockchain space. Intuitively, it is because you have somebody in the network wants to make a computational assertion, and rather than asking everybody else to redo the same computation, you can just post a short proof that people can check. Does this make some sense? All right. Now, the type of succinct arguments I'll talk about today are called transparent. Who of you has heard the name transparent here before? OK, Louis, you work at StarkWare. I'm glad that you've heard it by now. So maybe I'm not going to highlight it too much in this particular talk. Let me just say that many constructions of succinct arguments that have been deployed that are part of real technologies today, they have a rather inconvenient so-called setup, which means that before you get started proving and verifying proofs, somebody that is trusted has to prepare some public parameters for the system in the sky for everybody to use. You can think about it as some sort of the equivalent of like an RSA modulus, okay? Somebody has to prepare an RSA modulus and put it online for everybody to use, but then you have to destroy the secrets that were involved to create the modulus, okay? I've been involved in deploying some of these technologies. I can tell you it's a pain to put up these parameters because you're in peer-to-peer networks. There's no trusted party that can prepare these parameters for you. So these things can be handled in other ways. I'm not going to talk about it right now, but a lot of the excitement today is about deploying a new generation of succinct arguments that doesn't require this sort of setup at the beginning. We call these things transparent succinct arguments. Why transparent? Because all you really need is just some public randomness. So one way to obtain it is you take, I don't know, the digits of pi. You take the first 1,000 of them. They're random looking. That's good enough. And so nobody could have architected pi to kind of be evil for these constructions. So that's kind of public randomness that we can all agree on. Okay, so STARKs, which is the technology behind StarkWare, are a type of transparent arguments that are scalable, which means succinct and something else. So I'm going to give you a picture right now for that. So if so far proof systems didn't make a whole lot of sense, now I'm going to turn it into a picture, and hopefully that will make a little bit more sense. Okay? So we're talking about a protocol between a prover and a verifier. So here are a prover and a verifier. These are algorithms. Okay? The prover wants to convince the verifier of a certain computational statement. So you have a public function f, public input x, and the prover also has a private input w. Okay? And it wants to convince the verifier that this w that it's not going to tell the verifier is such that f of x comma w equals 1. Okay? What is an example of a computational statement? Well, maybe I want to convince you that I know the secret key corresponding to this public key. Okay? So this is a type of computational statement that involves a secret part I don't want to tell you and something public. And if I convince you of that, then you know that I am the rightful owner of a certain public key. This type of computational statement is not necessarily a large one, right? It's not a big computation. But there are other computations that I'm probably not going to talk about that are very interesting in the blockchain space, where the computation itself is very long. Okay? And so you want like short proofs for that. So the verifier knows the function, the public input, and in this case, the time bound. So there's always public parameters, and the proof is something written down. Okay, so it's a short proof that you send. So these proofs are publicly verifiable. Once you have them written down, anybody can check them. This is important for blockchain applications because you can include them in a transaction, and everybody in the peer-to-peer network can read them. That make sense? This is a non-trivial property because in computer science we have interactive proofs, we have privately verifiable proofs. These are publicly verifiable. They're transparent, so we just have randomness in the sky. And these are the main, really like important properties of succinctness. So first I want to draw your attention to the size of the proof. So from a sort of formal perspective, what you want is the proof to be exponentially shorter than the computation, right? So you have a computation of size t. Log of t is exponentially smaller, some polynomial in that, okay? We call this a succinct argument, okay? You also want that the verifier is going to check the proof in time that is proportional to it. So it has to pay log t, which is kind of the size of the proof. And obviously, it needs to know what it's checking, so it will read the program description, the function, and the public input, okay? So notice that this thing is much, much smaller than t for like interesting settings of parameters. The prover has to convince the verifier so to at least do the computation. So it's paying t, and then we want the overhead to be small. Okay? So this is actually the picture of a Stark. Okay? It's a rather simple interface. It's not a complicated protocol. It's two algorithms. The prover algorithm, verifier algorithm. Each of them is our function, right? It's an algorithm, takes inputs, produces an output. The output of this one is a proof. The output of this one is the decision bit. Okay, and these are their inputs. Are there any questions about this slide? Yes? So can you a bit louder, please?
Yeah, so just to make sure I understand you correctly, so t is supposed to be very large.
Yes.
Hard to prove.
Well, not hard to prove. Somebody's got to prove it, so particularly the prover. But it's something that you, as a verifier, are unwilling to do it, okay? Because maybe you're a computationally weak device, maybe you're a light client sitting on a network, and you're not willing to redo computations that are done by maybe full nodes, for example, okay? So there is some asymmetry of computational resources.
So T is like large, but not like,
yeah.
possibly large.
Yeah, we're not interested in computations that literally nobody can do, because then we cannot learn anything about them. There are, we can't expect to know about computations of sort of length t without running time t that you run into undecidability problems. We will not. So somebody's doing the work, this guy. So he has seen the whole computation. In fact, he does a little bit more than that. And that little bit extra work is to produce a short proof that certifies for that. You had a question?
Are these complexities constant for all STARKs? Or do they vary?
Well, this is the definition of a STARK. Then when it comes down to building an implementation and certainly building products, you're going to be very interested in what's the poly here? What's the poly here? What's the poly here? Right? So you want these things to be pretty small. Roughly speaking, you have a couple of, you have log squared, log squared, log squared. We know how to do these things rather well. Okay. Now, in terms of interface, is it clear why this is a non-trivial goal? Okay. So you take long computations, you shrink them down into something exponentially small, okay, and you get to check it. All right. I don't have slides specifically about why these things are useful. Again, intuitively, you should think about somebody. Think of Ethereum, okay? In Ethereum, everybody's executing every smart contract call, right? So the entire network moves at the speed of the slowest node, right? It has to, because everybody has to execute the call computation. So imagine a sort of Ethereum prime, where instead, you just put a proof that the computation was done correctly. Now, everybody else is only checking the proof. So you can move at the speed, but you're not bound anymore by sort of the expense of the computations, right? All right, so this is a very powerful tool. Like it's easy to describe. Achieving it's a different story. STARKs are very hard to construct. It involves many steps. But like many complex things, it's made up of design principles and smaller pieces that are easier, right? So when you see, I don't know, a big building or a bridge, it looks complicated, but somebody thought about it, and there are small chunks that you can understand, and when you put them together, it makes sense, okay? So what I'm going to do is peel off the first layer, okay? And it's going to be actually a cryptographic layer. Underneath, there's going to be something information theoretic. So what I'm going to do is I'm going to assume something information theoretic I'm going to define. And then I'm going to show you how, with absolutely bare bones cryptography, just hash functions, you can obtain a STARK from that. So it's like a reduction. And then I'm not going to tell you about where you get that information theoretic object. That's a different story, okay? But at least you see the last sort of layer of construction. And in fact, the only place where cryptography comes in. Okay, so that's kind of the goal of the talk. So how to build STARKs just based on hash functions. But the fact that you only rely on hash functions is rather important, because it's pretty much one of the only ways that we now can construct succinct arguments that are also post-quantum. So the current constructions are rather, to my mind, like basically unbreakable. So these paradigms will stick around for hundreds of years. I mean, there's nothing we're using about number theory, lattices. There's just like hash functions, okay? All right, so it seems like pretty daunting. I just have a hash function to build a STARK, right? So, but yet actually I can do it with pictures. So, so the plan is I will first describe a way to obtain a STARK using a pretty simple object called the PCP. Has anybody heard the term PCP? Wait, one person, okay. It's okay, I have pictures for everything. Then I'll mention that today we do things a little bit differently for constructing efficient STARKs. Then I'll conclude. Okay, and probably I think I'll just mostly go through 1 and 2. So I'm going to describe a different type of proof system. It's going to look different because I said it's different. It's not a cryptographic object, okay? It's actually something that literally exists. We don't have to make any assumptions. We don't have to borrow anything from nature. It's called a probabilistically checkable proof. This is one of the sort of probably one of the most important achievements in theoretical computer science in the last 30, 40 years. It has lots of applications, and here's going to give you a picture for it. So look, there is again a prover and a verifier, but now they're going to interact in different ways. Instead of the prover outputting a short proof, guess what? It's going to output a very long proof. Okay, so this proof, instead of being poly log t, is going to be poly t. That seems like, why would you ever do that, right? Just put a proof, output a proof that is much longer than the computation it attests to. Well, the point is that this proof, by virtue of it being longer, has redundancy that is useful, and it enables the verifier to probabilistically check it. So there is a way for the verifier, after the proof has been written, to pick at random some correlated ways, some locations, read them in some random access way, get the answers, and make up its mind. Okay? So this is a probabilistically checkable proof. It's a proof that can be probabilistically checked. So it's kind of dual to a Stark in that the proof is long, but you don't get to read all of it. All right? Okay, so I wanted to explain. Okay, the picture looks different. Can anybody maybe explain why this is not quite a Stark? I'm going to maybe start saying SNARG because I don't want to emphasize the transparency right now. But is it clear why this is a different object than the previous picture? Maybe to sharpen it, let me propose to you a protocol that looks like a Stark, okay? But I'm going to tell you it's not secure. What if the verifier has a bright idea? It says, you know what, prover, don't send me the proof. I'll send you my questions, and you tell me the answers. So overall, if I just cut here, the communication that we'll have is going to be pretty small, right? And let's take that to be our communication transcript. Maybe that's going to look like a Stark, right? So I tell the prover, here are the locations I care about. Don't send me the long proof because I can't read it. Just tell me the answers for these locations. Is this like a reasonable way to kind of not have the prover send the long proof? Yeah?
It has to be random.
The verifier can pick these locations at random, yes?
Yeah, but then he doesn't know that the prover is showing him, right, the spots that he wanted to look at.
Yeah, so the prover basically learns the locations that the verifier is interested in before it has written down the proof, right? This is kind of like saying, I challenge you to guess the outcome of a coin, and I first flip the coin, then I let you guess. So you always win. So the point here is that the security of this object relies on the fact that first the prover writes down this thing, and then, independent of that, this one flips randomness to choose the queries. If you first see the queries, you can always complete kind of answers to the queries in a way that makes the verifier happy. Okay? So somehow there's a question of order here where the prover can't send the proof directly. I mean, like in this model, yes, we can, but then we want to use this object. We can't send the proof, it's too long. We cannot have the verifier ask for the questions because the prover is going to cheat, so what do? Right? So we're going to bridge between this model and the Stark using hash functions. Okay? And I can do the picture. Is it clear what the issue is? I'm just assuming this thing that looks useful. I'm just pointing out it's not what we want. Why? Because of this thing. And I'm going to show you how to use hash functions to go from here to a Stark. Okay? So actually, this construction is pretty old. It's sort of yes.
What is, maybe you said it, but I couldn't get it. What is the difference between a SNARG and a Stark?
Yeah. So the T there specifically denotes that it's transparent. Right now, I'm just trying to achieve some cryptographic proof that is succinct. And SNARG is just an acronym for succinct non-interactive argument. Okay? Which is an argument that is succinct and non-interactive. And really here, I was trying to build an interactive succinct argument, and it's insecure to build it this way. I'm not going to specifically emphasize too much this one right now. I really want to just get across first this how to use hash functions. So there's a beautiful construction from about 25 years ago that it does exactly this. It takes you from a PCP to a SNARG. These things weren't called SNARGs back then, but people definitely understood why they were useful. By the way, when I say hash functions, I specifically mean something precise. In cryptography, we call these things random oracles. What is a random oracle? It's just a random function, okay? And in your mind, you can think about SHA-256 or Blake or your favorite cryptographic hash function. The point is that the specific instantiations we cannot mathematically analyze because those are like things that people build. But when you want to analyze stuff, you have to idealize it into a random function. So if you remember, the interface of a SNARG was a prover that spits out a short proof that is read by the verifier. So what I'm going to do now is I'm going to fill in with pictures what the SNARG prover will do and what the SNARG verifier will also do. Naturally, I will use as subroutines the PCP prover and the PCP verifier because that's all I have like currently in my pocket. In the other pocket, I have a hash functions. In the other pocket, I have a PCP. That's all I can use, right? So what am I going to do? Well, first I can run the PCP prover to write down the PCP. Like, what else am I going to do, right? But now I have an issue, right? I can't send it, and I have to somehow I'm going to have to somehow like figure out locations the verifier wants, but the verifier doesn't trust me to like first write down the PCP in my head and not change in my mind once I see the queries. So now we can use something called a Merkle tree. Who has heard of a Merkle tree? Right, more than one person. That's great. So that's about 50%. So when you have a hash function, you can build a Merkle tree, which means that you pairwise hash each location. Okay, so you take the first two, hash them together, you get like a parent, right? And you do it like this. So you get half the locations now above. You keep doing it. You keep halving, halving, halving until you get a so-called Merkle root at the top. This you use with the hash function. Once you have the root, that's some sort of small commitment to the long PCP, right? You can take this small commitment and itself fit it in, put it as an input to the hash function again, and what are you going to get out? Random-looking garbage, right? Randomness. You can take this randomness, and you can use the randomness to derive queries that the verifier would have asked. Remember, the verifier was a randomized algorithm. I can just take the output of the hash function and treat it as the verifier's randomness. And kind of, as an argument prover, I'm simulating the verifier in my head. And notice that the randomness is on purpose made to depend on a Merkle root. So that once you see the randomness and you say, I know how to change. I come back here, I'm going to flip this one to make the verifier accept. It's going to change everything. And my randomness is going to change again, right? So taking the commitment and plugging into the hash function to derive randomness enforces this kind of time precedence of first writing a PCP and then deriving the randomness. Once you have the randomness, then it tells you which locations it wants to access. Once you know those locations, you can prepare the so-called authentication paths. Because if you want to reveal, and I want to say, hey, the first location has this value 3, I could just lie, right? I have to like convince you that 3 was the thing that was written here, right? So in a Merkle tree has this property that if I give you this value, and that value over there, you can check yourself by kind of hashing together the kind of siblings on the path from you to the root that it is consistent with the root, right? So then in the end, what I send you, the SNARG that I send you, is the Merkle root commitment to the PCP and answers to all the queries that you want that are supported by authentication paths relative to that root. Okay? This is a written down proof, this small, I can send it. On the other end, as an argument verifier, what am I going to do? First, I receive all this stuff. At the very least, I should check that all the paths check out against the root so that the values that were claimed are certified. And secondly, I will simulate in my head the decision predicate of the PCP verifier using the randomness that is derived from the root. And I will feed it the answers that were given to me, right? So intuitively, what the argument proving is doing is using a hash function to do like a secure pre-sampling of the PCP. It kind of filters the PCP to answers that are kind of provably derived in a way that is independent of the PCP, because the randomness is derived from the commitment to the PCP, right? Okay, so this construction is a SNARG. Why? Because on the one hand, the size of the PCP has some length over some alphabet, but the size of the SNARG, this thing, depends on the number of queries you're making, right? Then, of course, you have some answer. If your alphabet is binary, this is just like a bit. And then you have the size of the authentication paths, which are logarithmic in the size of the PCP. So this entire thing, the amount of communication you're sending, is just log in the PCP length and linear in number of queries. Okay? And if we go back to our picture of a PCP, the whole point was that this one is poly t, while log of that is log t. So that's OK. And the number of queries should have been small. And PCP is actually, you can construct them with a very, very small number of queries. In fact, as small as 3. Okay? So overall, the communication that you have here is small. Of course, this also needs to be proven. One can prove that this particular construction that I wrote is, in fact, secure in the so-called random oracle model. This means assuming the hash function is ideal, behaves like a random function, this entire thing really is a SNARG. Okay? I have some technical notes there, but I'm not going to talk about them right now. This is actually a rather simple construction of a SNARG. All you really need is a PCP, and boom, you have it. Okay? Question? Yeah.
Yeah, so if I understand you correctly, so the algorithm would first have to get the Merkle root and then ask the queries, right?
Yeah, and it asks the queries in a particular way. You feed the root as an input to the hash function to derive the queries. It's like a deterministic derivation procedure, and because the output of the hash function is like random looking, you treat that as randomness.
Okay. Oh, so you use the root for your queries, but then can't the prover know your queries in advance?
But it's too late.
Oh,
because
it's already
yeah, so once you see the randomness, you say, I know how to cheat. You come back here, you change it, but now it's not consistent anymore. You won't be able to certify the other answer to that root, right? So, and then if you try to change it, it goes back to a different root. You plug it in, you get different randomness, right? But anyway, these are things you can literally try to do. You can try to chase randomness around, and that's part of the security reduction that says that whatever damage you can do by this type of reasoning is negligible, okay? But there is something you can do, okay? In particular, you can just try to run this multiple times, right? So if you do it 10 times, you have 10 times the probability of convincing the verifier than you had before. But 10 times is OK, because 10 times negligible is negligible, right? Good questions. OK, so this is the simplest construction of a SNARG, OK? Doesn't use anything but hash functions. A separate story is where do PCPs come from. I teach a graduate course, which is like a semester, and then you learn about constructions of PCPs. There's not, for tonight, it's a rather complicated and beautiful subject. More questions about this picture? Yeah?
What do the time steps figure into this?
The time steps.
No time steps.
There's
Earlier you said that we were supposed to be able to show something within a number of time steps.
Sure. We need to make sure that the prover is efficient. Right? So I only argued about the size of the proof, right? So let's look what the prover is doing. The prover is just running the PCP prover and then hashing stuff. Hashing things is easy, it's linear, right? So kind of really the cost is producing the PCP, okay?
Yeah, but the tree it's deterministic, right?
Yeah, the tree is easy, right? So once you have it written down, it's a linear time cost, right? Hashing something of size n costs you like 2n.
Is the tree changing in any way?
No, it's a hash function. You just pairwise hash it. So if you have something with n cells and you want to build a Merkle tree over it, it will cost you 2n hash invocations. These days, a hash invocation is 1 cycle in a computer, so that's really fast. So really, the dominating cost of the SNARG prover is the PCP prover, which, you need to make sure that it's efficient, right? So important research goal that people have worked on, and we know the answer, is to make sure that this thing runs in time that is t times a small amount, okay? Similarly, on the verifier, he's not doing much of anything. He's just checking a few authentication paths. Each of them are of size log L, right? So which is log T. That's small. And then he has to run the PCP verifier, the decision predicate. And again, you have to make sure that the decision predicate with the PCP verifier is fast. And that's something that we're assuming away for now. But the point being is that in this construction, it's pretty clear that the time complexity of the argument prover and argument verifier is dominated by the time complexity of a PCP prover and PCP verifier, okay? So kind of you pushed the problem down one level. Okay, right, good question. All right, so I am 1 minute shy of the 30 minutes. So what I want to do is mostly wrap up. So I mean, I could go on longer, but I want to. Actually, we have a choice. Okay, I do want to have a break of 10 minutes so you can get your pizza, so I could either explain how modern Starks are constructed. Okay, that will take another 15, 20 minutes, and then we can just call it not a day, but a night. Or I can start talking about a different paper about other constructions of SNARGs. Okay. I vote for continuing this presentation because we have state, so we don't have to talk about some other thing, but open to other, yeah? What? Option one, okay. But the pizza is here, right? Not yet? Okay, so we'll continue for now. So we'll break at the pizza. Okay, but we are at the 30-minute mark, and I'm aware of that. All right, so also I should point out that this construction has I want to come back to the transparent part. So if you want to use this, say, in a system, in the real world, what do we need to agree on in terms of system parameters? We just need to agree on which hash function to use. Okay? That's pretty simple. You just decide SHA-256 on this initialization vector. The initialization vector should be random. So that's it. There is nothing complicated about setting it up. If you haven't been digging into SNARK constructions, then this looks like, so what? Duh. But there's many other SNARK constructions that have been deployed where we need to agree on parameters that are very difficult to generate. So this is actually like a very big plus. We're only making use of very simple cryptography. This is, again, like rather special because many other SNARK constructions either use pairings, which come from elliptic curves. They will make use of groups of unknown order, like rather complicated algebraic constructs. Here, you just need some like hash function that does bit twiddling and looks random, right? So it's a much more sort of unstructured and easy to come across cryptographic object. Oh, I did have actually 2 lines about the running time. I already explained it, so I'm not going to talk about it again. But doesn't anybody have any intuition about why this is post-quantum? One can actually prove is this construction is post-quantum. What are quantum computers typically good for? Kind of, but that's not technically quite true. They do things in parallel, but when you want the answer, it collapses and you need to orchestrate things right. So they're not just about parallel.
The efficient Shor array.
Right, so there is a Shor's algorithm. So and there, what they're great at is computing periods of periodicity of cyclical structures. And in particular, they're very good at factoring integers, extracting discrete logarithms. So a lot of cryptography that is based on number theory just fails in the face of quantum computers, specifically because there is structure that is kind of cyclical. Here, because we're just using hash functions, we have hash functions like SHA-256 that are just an S box after an S box after an S box and just like messy things in between. They have, by design, no nice mathematical structure. Okay? And we have absolutely no idea how to use a quantum computer to make a dent in any of these constructions. So the paradigm I just described is post-quantum in the sense that you can just plug in any sort of already existing hash function. You just need to tweak parameters a little bit to take into account for some polynomial speedups of quantum computers, but otherwise these things, one can prove, are secure against quantum computers. So it's a paradigm that should serve us well for quite a while. All right, so the pizza has arrived. So I'm going to maybe conclude this particular slide and we'll continue later by mentioning, I said many good things about this construction. There's one tiny problem, which is the PCPs, which I assumed away, are like really expensive. Not asymptotically, like we know like asymptotically they behave nicely, but in terms of concrete constants, like the kind that we care about in the real world, they're horrible. Okay, I actually have done research in this direction, and made some progress, but it's just like a hard problem. So And indeed, this particular construction has been basically sitting on the theorist sort of shelf, but hasn't really made it into, in terms of technology, for a long time, precisely because of this reason. PCPs are very, we can call them galactic algorithms, mainly like the instance sizes at which you start benefiting from their asymptotics kind of exceed kind of the size of the universe or things like that, right? Because just too difficult constructions. Yet today we have efficient STARKs. So what are we doing? We're doing something else. So let me tell you about another way, similar to some extent. So today, one can build efficient SNARGs in a similar way from a different type of probabilistic proof. Okay? Instead of being a PCP, it's going to be something else called an interactive oracle proof, IOP, that is the acronym. This is a notion that I introduced with my esteemed colleagues a few years ago. And it's actually a pretty simple notion. It's kind of surprising that it wasn't defined and studied until recently. As before, we are going to have a prover and a verifier. And it's going to be similar to a PCP in that it will involve long proofs that are being exchanged. But these long proofs will be exchanged rather than written down and that's it. They will be exchanged in an interaction with the verifier. Okay? So you can think about it as some sort of multi-round PCP. The verifier sends some challenge to the prover. The prover answers with a PCP. This goes on for some number of rounds. More challenges get sent, and more PCPs get sent. Okay? So it's like a multi-round interaction. Each round introduces a new PCP. And at the end of the interaction, the verifier gets to query at the desired locations any of those long strings. Okay? It's clear that this is a strict generalization of the previous PCP model. Okay? We call this an interactive oracle proof because it is an interactive proof where the things being exchanged from the prover to verifier are oracles. Okay? These kind of random access to strings, we call these things oracles in computer science. Okay? Because you can kind of query at any desired location without paying for their length. All right. So here we have a lot of room as in terms of, you can think about it as design space. Before, all we had was randomness and probabilistic checking, but now we also have interaction. Okay, that's kind of a new computational resource. However, you might wonder, hey, look, this is pretty similar as before. Can we do new things? And in fact, another concern is, can we still translate this into a SNARG, right? So there's two concerns, right? We have a new model, something more general than the PCP. We should first convince ourselves that we can still turn this into a SNARG. And second of all, it would be good if this extra design space buys us efficiency. That's kind of what we were missing before, right? So let me first, by picture, convince you that you, in a way that is analogous to before, you can go from IOP to a SNARG. Okay? So again, similarly to before, I'm going to put down the argument prover and the argument verifier. And we're going to fill in what each of them does. And not surprisingly, they will be using the IOP prover and IOP verifier respectively as subroutines. So the argument prover will start simulating the IOP prover in its head. The IOP prover is going to expect some challenge to even get started, right? That's kind of what the model was saying. First it receives a challenge, then it outputs a PCP. So now the argument prover is in his head. It's like, I need to fetch a challenge, a sort of good-looking one. What am I going to do? Well, for example, it could apply the hash function to the statement being proved. Something will come out, garbage-looking things, and you call that randomness. Okay? So that's the randomness you feed to the IOP prover. At this point, the IOP prover is going to spit out its first PCP. What are we going to do now? We can't send it. We're going to have to do something with it. What are we going to do? The hash it in a Merkle tree, right? So boom, like we pairwise hash it, we get the first Merkle tree root, right? Now we're not done, right? Because the IOP prover is going to keep spitting out PCPs. Okay, this example, I'm going to have two PCPs for concreteness. And I have to feed him with the next challenge. Okay, so I have to, as an argument prover in my head, I need to derive the next kind of good-looking challenge for the IOP prover. So what I'm going to do, I'm going to take the previous root and also use the previous randomness to derive the next randomness. Okay, so I'm kind of depending on both. All right? Because you don't want randomness to kind of be unlinked to the round where it's supposed to be, right? You kind of put them in order.
And you're also prolonging the memory of the system.
Prolonging the memory of the system.
Because now it has to be connected to the previous.
Yeah, so that's why I'm putting them in a, basically there is a hash chain on this side that keeps in order all of the sort of challenges, right?
Yeah. And in information theory, you can gain something else.
You cannot reorder things because of the hash functions.
Right.
Yeah.
But you also get some previous memory.
I'm not sure what memory means. Oh, I can talk about it later. So now I have a new randomness. I feed it to the IOP prover. And now the IOP prover will say, OK, here's my next PCP. What I'm going to do, I'm going to Merkle hash it again, get a second root. I derive more randomness because I'm going to need more randomness to derive the queries. Now these queries are going to be to either PCP, really, right? Just some small number of queries to this one, small number of queries to that one. And in my SNARG, I'm going to have to certify all of these. So I'm going to prepare a short proof that contains both roots for both PCPs. And then I'm going to authenticate whichever query against whatever root it was supposed to be, right? So let's say if A1 is this one over here, I'm going to provide the authentication path that certifies this location. That authentication path consists of this location, and that location, right? They will certify against this root. If this one was for the other one, then I'm going to be the authentication path inside that tree, right? And that's what the argument prover does in its head. Basically, it is simulating in its head what the IOP prover would do, and it compresses down each of the PCPs, making sure that all the challenges are derived in a kind of time-preserving way. Okay, simulating a real interaction. Yeah?
So the NP can be decomposed to different small statements?
What can be decomposed?
Like the large NP statement can be decomposed because there are different PCPs.
I'm not assuming anything right now of what these PCPs mean. I just have they will be something when you construct it. But right now, all I'm saying is that I have a multi-round PCP. It's doing something useful for the statement that I'm trying to prove. And I just take it as a given, and I run it, right? And my job right now is I need to make sure that I preserve security. So I'm now using the hash function to make sure that all the randomness that is used to simulate this is like good randomness. So I derive it from the hash function, and I derive it in the right order, right?
Number of iterations, it's agreed between them?
The number of iterations here is the number of PCPs. But remember, this interaction is happening all in the prover's head, right? So there is no interaction yet with the verifier. I'm just preparing eventually. All this information will be written down into like one proof that it gets sent. Now the verifier, what is it going to do? It has to check all of the answers against the corresponding roots. So as I said earlier, if the first question was supposed to be for root 2, it will check it against that one. If the second query was supposed to be against the first tree, then it uses that tree's root. Then it has to rederive all the randomness in order. So it first feeds the first root, then the second root, like all of this in order, right? And then it derives the randomness for the decision predicate. You provide all the answers, and it makes up its mind. Okay? And one can prove that this thing makes sense, meaning there is a security reduction that says that if the hash function you're using behaves like a random function, and the IOP underneath is an IOP, that's secure, then these two things together will give you a SNARG. Okay? This is believable, right? I mean, we already discussed the earlier construction. It was doing it for one PCP. Now we're doing it for multiple PCPs. So we're kind of repeating that paradigm, and we're using a hash chain to keep things in order. That's really all that's happening. Okay? So what have we gained? Well, first I want to remark that we didn't lose any of the good properties. This thing is still transparent, meaning that all we need to do is to just agree on the hash function. I haven't really used any new cryptography. I'm just using a hash function more. I'm still making, sort of this lightweight use of lightweight crypto. I'm only using a hash function. One can still prove that this thing is post-quantum. But now we have a much bigger design space. To get started, it suffices to design an IOP. Okay, every PCP is an IOP, but not every IOP is a PCP. So there's a bigger set from which we can fish, right? And because we can fish in a much bigger set, maybe we can hope to get better constructions. All right? So this leaves the question of can one indeed design IOPs, these multi-round PCPs that are sort of more efficient than PCPs? Because if so, then we'll be pretty happy. Okay? Yes?
Didn't you define IOP as consisting of several PCPs?
I did, right? So by picture, but here it is.
How can that be more faster?
Well, you can do more. It is, like if you look, this is the set of PCP. The set of IOP contains it. And if you have a complexity measure like running time of the prover, you have more constructions to choose from, right? So it's like a bigger design space, right?
You still need to do PCP.
And no, I can.
The number of quarries can be different in each time.
When I say in each round you send me a PCP, I don't mean like when I say, I mean it in the informal sense, because it's not like this one is literally a PCP that by itself makes sense. It makes sense in the protocol, okay? So what you're sending me is a long string that I can randomly access using those queries, right? But it's not like if I cut the protocol short after the first round, that is a PCP, okay? So you see, it's just syntactically, I can do more. It is a bigger design space, right? So, if I ask you, to dribble in basketball and I give you one hand or two hands, there's more things you can do with two hands. In particular, you can only use one hand, right? But you can do more things with two hands, okay? Here, I give interaction. So it's an additional degree of freedom. You can go ahead and take advantage of it, in principle. Now, then, now we need to talk about whether this is something that, because with the example of the dribbling, if I give you two hands and I give you an extra finger on one of the hands, it's pretty similar to what you can do with two hands, right? Two hands, 5 fingers on each hand, or two hands, 5 fingers on one hand, 6 fingers on the other hand. It's not clear you can do many more things than you could before, right? So it has to be like qualitatively more. So the question here is, are IOPs really more efficient than PCPs? Okay, not just in principle, but in terms of like concrete constructions. And so this brings us to efficient STARKs in the sense that what we want is to construct these STARKs. Like I've just described you this kind of, you can think about it as a compiler that takes a hash function, an IOP, and gives you back a SNARG, right? And because this construction, as I already remarked, preserves basically the efficiency of the underlying PCP/IOP, if we want good efficiency properties like good scalability for the STARK, all we really need to do is to have good efficiency for the IOP. Okay, I'm just like restating the fact that what we want are efficient IOPs. And actually, after introducing this model a few years ago, there's been a lot of research to precisely explore what can we do with interaction that we couldn't before that is interesting. Okay, and so I personally have worked a lot, really a lot in the last few years to explore this. And there's been many new techniques. Here are some buzzwords that are techniques that are somehow inherent to the IOP model. We don't know of analogs of these things in PCP land. And by virtue of having these new techniques, we are able to get some pretty good sort of parameters. And I'll give some examples, okay? So earlier I was talking about the running time of the prover. And I was saying, look, the prover should be t times polylog t, right? Not much more than t. Guess what? we actually know how to construct IOPs where the running time of the prover is literally t log t with a small constant in front. That's like pretty good. It's like almost linear. You're going to have to pay t just to run the computation. And this is like the cost of producing the proof, log t. And there's evidence that we are nearing in the next year or two, we can get this down to linear. Okay, but it's already very good. The running time of the verifier, here I didn't really make it very explicit, but the point is that if you want a security parameter k, so say think about k as 120 bits of security, you're going to run the verifier, say k times. Think about it as different queries each time. And okay, here I didn't really make it explicit, but it's roughly log squared. Okay, the proof length exchange is actually linear. This is optimal. Okay, so if you look at all of the sum of the PCP lengths in the interaction is actually linear. It's a small constant. It's like 6 times t. Okay. Number of queries, we can actually make it to be like essentially optimal with 128 bits times like some small constant. I say theory in the sense that really I was talking about theoretical constructions. In practice, the kind of things that really run fast, the main caveat is that we have an extra log t. And these are research frontiers. But the point being is that for PCPs, we absolutely have no idea how to get any of this. In fact, even for something like just getting linear proof length, linear size PCP, we don't even know how to get anything close to like polylog t for queries, regardless of running times. And that's like a major open question for PCPs that likely is not going to get answered for a long time. But for IOPs, we know how to get linear proof length. This is an example. Okay? So both theoretically and correspondingly in practice, we have a lot more efficiency that we gained through this interaction. Okay, so I'm at 17 minutes after the break, and I think I'm going to summarize here. So what I have explained is a generic transformation that takes a multi-round PCP called an interactive oracle proof and any hash function modeled as a random function, and it gives you back a SNARG with lots of nice properties like being transparent, lightweight, and post-quantum. This is the paradigm that you can put together with efficient IOP constructions that will give you efficient Stark constructions. Okay? So, and a lot of the sort of less picture-friendly sort of techniques are in how do you actually build these things. Okay? Like what algorithms and protocols go behind constructing efficient IOPs, but that's not something that I can talk about in this audience. That's sort of, you need to have some background in computational complexity theory, in algebra, and so the error correcting codes. So there's a lot of and more that goes into constructing those type of objects. Okay, so I think I'm going to stop here and take more questions, if there are. Yeah.
Can you explain how efficient Stark improve privacy?
Oh, yeah, so let me talk about privacy or efficiency, because I didn't really talk.
Privacy.
Oh, privacy, for me, it's a simple example because we can just say example Zcash. For those of you who don't know, it's a privacy preserving digital asset transfer, okay? All you really need there is a zero knowledge succinct argument of knowledge, okay? And this gives you such a thing, okay?
Zcash might be different from, we talked earlier, you said that this could be used on any other decentralized network, right? So how using this on any other network could change privacy? Because from what I understand, it provides a more efficient proving mechanism, but don't necessarily change anything on the transparency or data kind of, whether the actual transaction data is available publicly or not.
Okay, but I want to take a step back and say that when you reason about privacy, in peer-to-peer networks or whatever, so somehow you take kind of a SNARK as a black box, a zero-knowledge SNARK as a black box, and you design protocols with it. Now, it's like using a hash function, right? The hash function needs to be put to use to something, right? So today I described a particular type of ZK SNARK. So the fact that we looked underneath and saw what's underneath doesn't change what it was. it was and continues to be a ZK SNARK. So whatever we could do before with ZK SNARKs, in principle, we can also do with this. Except that this has additional properties that we didn't know how to have before, like being transparent and post-quantum. For example, the current today's peer-to-peer network in Zcash uses a ZK SNARK that is not post-quantum. Okay? So there's a type of capability that is brought about by this type of technology that is not existing there. Now, what else can you do for privacy with these knowledge proofs? But there's an entire cottage industry of projects and ideas that explore, once you have a sufficiently efficient ZK SNARK, there's plenty of things you can go about by designing protocols. You can do, I don't know, private decentralized exchanges. You can construct dark pools. You can do anonymous credentials. You can do like anonymous voting or whatever, right? So, but each of those, it's not like an immediate application. It is within the realm of cryptographic protocol design, which means, you know, you sit in your chair, you have a shelf, and on the shelf there is digital signatures, there's encryption, right? All these kind of classical tools, and now you have a new shiny tool, ZK SNARKs. And now you sort of sit down, you try to see what it is that you wanted to do, and you design protocols for useful things in privacy. Let me also touch a little bit about efficiency. These type of constructions that I specifically talked about today have implications to efficiency that we didn't really have before, mostly because they don't have a so-called setup. Because there's no setup in advance, you can actually run these proof systems on rather large settings of T, which is not here anymore, but the size of the computation. So you can actually compress very, very large computations. And an application that we have explored at StarkWare is a batch proving of transactions. So you can think about, for example, in a decentralized exchange. Today, typically what happens is every atomic swap between two parties that is countersigned on both sides has to independently hit the blockchain, right? So there's some smart contract somewhere that stores account balances, and it gets updated every time there is an atomic swap signed by both parties. And now suppose that there is many such atomic swaps, like the network will just like collapse in processing them, okay? Also individually, it's expensive. Like each contract call, you have to pay for the damn thing to be processed, right? And it costs you gas. What you can do instead is line up a bunch of atomic swaps in one batch and prove using something like this one that you have seen all of them, you have verified all of their signatures, and you have updated the account balances properly. And then you have this short proof that is exponentially smaller than the batch, and you ask the contract to just verify that. Okay? So that's an example of something that would have been hard to do with the type of SNARKs that are currently deployed in Zcash, mostly because those type of SNARKs require some so-called pre-processing, I don't want to get into it right now, that would have been too expensive to do for such large computations. So this is a type of construction that is suitable for batching purposes. Okay? Right. More questions?
You just answered my question at the end of that. Like if you could put it in the context of a real transaction, where you have a specific data block that you're adding to the blockchain, you're trying to impose on the blockchain, if you put it that way, across the network. So how would you put this algorithm into context with that? Where does the data fit into this? The data that you're actually, not some random hash that you're creating, but the data that you're actually communicating to the rest.
Yes, I think the example of atomic swaps is, I think, a good one, right? So you have kind of the strawman solution, kind of the direct, sort of straightforward one is you just have a smart contract that keeps track directly of all the account balances, and they get updated every time you process an atomic swap. The gas cost per atomic swap is pretty hefty, it's about 200,000 gas. And also, if you want to process a batch of atomic swaps, it will cost you number of atomic swaps times 200,000 gas. This is without any proof systems. What instead you can do is you can say, look, I will off-chain run a prover that will check that all the atomic swaps carry proper signatures. All of the instructions as part of atomic swaps of which sort of tokens change hands have been updated in a database. And now instead of checking all the signatures and check all the balances, just check the proof. And then it attests to the state transition. And because the proof and checking the proof is exponentially faster than the computation it attests to, the amortized cost for this will actually go 10 to 0, okay? Because it's log T over T.
Or use the payment channels.
Or you can use any of the other solutions that have different threat models and different architectures, and there's a very wide sort of design space that, when you do systems engineering, there is sort of a lot more into consideration beyond the specific security properties of a particular cryptographic primitive.
But one of the nodes must do those computations.
Yes, but you don't trust it to do it because it's a prover. And the security property here says that you don't care who does it as long as somebody does.
At least a second node must do it too.
No,
Never.
no. You just need somebody to check the proof. So
Verify.
yeah, to check. Yeah, you just have the smart contract check the proof. Nobody else has to do it again. That's the point of cryptographic proofs, right? These are not toys. These have extremely strong security guarantees. It is, they have the following guarantee: either you are saying the truth or you broke cryptography. Okay, so there's no other way. Okay, so it doesn't matter whether Darth Vader produces the proof or your grandmother, right? They're both equally trustworthy from the perspective of cryptography. If you have a proof that was produced and it checks out, it doesn't matter who produced it.
So even if one node completely just it can generate hashes based, but without actually doing the proofs, right? It'd be the fastest, let's say, to propose some new transaction, set of transactions.
Yeah, I mean, it has to produce a proof, right? Because you have to check something, right? So the smart contract.
The proof is a Merkle tree.
No, the proof is involves Merkle trees and other things, right? The PCP or IOP or whatever, right?
So being able to identify a certain path in the Merkle tree, essentially.
And there is the PCP underneath. Like these queries are not just random queries; they are designed to have a certain security guarantee. Again, the security guarantee is that,
You still have to find that specific piece of the transaction.
yeah. So this is not something that can be broken. Like this is you will either have to break SHA-256 or say the truth. So pick which, right? So.
And actually, in blockchain technology, there is one prover and there's a lot of verifiers. So, in case of efficiency, the verifier's time is more suitable to produce. And as you said, it's the least efficient link that will take the time. We will say, okay.
Yeah, so all the nodes in the network have to do something cheap.
So right. Yes, this is our. This node is the slowest in the system. This one proves. This one has to be to prove it also. So this what counts.
Wait, no. So the proving time is off chain, right? So whoever had
no, the proving time and
the verification.
The verification time.
Yeah.
The proving is one
person
per system.
Yeah.
I think I understand it because you're doing this in a very short amount of time, and I know you do this in class. It's serious.
Yeah. So
But let me ask you if this is correct. If my conclusion is correct. So the structure of the transactions has to be predefined. There can be no variation in the structure. There's no room for extra strings of comments or some other kind of little bits of data. It has to be specifically, everything's focused. There's a person, a transaction, the entire structure is predefined without any kind of extra data at all. Otherwise, this doesn't work, obviously. I mean, to me, it doesn't.
I mean, there is a format for the proof, right? And there is a canonical algorithm to check the proof. And that's what you have to put in your smart contract to check the proof.
Yeah, it has to be exactly, there's the person, and that person has a hash, and the transaction has a hash.
You run this algorithm, yeah.
All of the little details, there's no room for extra strings.
No, I mean, you can put a picture next to it if you want, or another string, but those mean other things, right? As far as checking the proof, that's the proof, and this is the algorithm, and this will go into a smart contract, and the smart contract will parse the proof out of whatever transaction it's sitting in, and it will check it, right? And once it checks it, it knows that whatever computation was done, it was done correctly.
Yeah. So okay. Right, because you do an inquiry, so if you ask who the transaction, who the party was that
produced it?
Party,
doesn't matter.
Party, whatever, any kind of query, then that's a specific hash of a specific person. There's no room for extra data. That's my question. Is that correct?
Yeah, I mean, it's not a question of room for extra data. It's just you can put extra data. It just doesn't matter for the proof system, right? So,
Right, it doesn't matter for the proof.
Right.
The verifier has to know that it's deterministic functions that does this proof.
No, you don't need to assume anything for the prover. What I'm describing here is...
The verifier needs to know that this is the way that the prover works.
No. I'm describing the honest prover. This is how the honest person would do it.
Yeah.
The point of a proof is that it works regardless of how this proof was generated. So a malicious prover can just try to fool you by standing on one leg, closing one eye, writing with the left hand instead of the right, or doing any of possibly smarter things, okay? But you don't care because you have the verifier. And the verifier has a guarantee that if it says it's happy, then whoever wrote the proof either broke cryptography or said the truth.
Yeah,
This is just a suggestion of how, if you want to say the truth, then I can tell you how to make the verifier happy. Otherwise, here's a very secure verifier. It always says no. Always, right? So then it's very secure. Like you cannot, by definition, make it happy.
The
So,
thing,
yeah.
the verifier has to know the format. This is the RT1.
Yeah.
RT2,
So,
and that's what I think answers this
sure.
question.
Yeah. Okay. More questions?
The proof size is O of T, right?
No, log T.
Yeah. The proof size?
Yeah. So okay, there are two proof sizes we're talking about. There's this argument size, and then there's the proof size of the PCP. These things are long. That's why they're long in the picture. This is short. So think about log T, T.
And it's a lower bound, right?
We cannot get PCPs shorter than T. Otherwise, funny things happen in computational complexity. Thank you for the good questions.